So I'm going to tell you a story of twisted cuprates. And this is an idea that came to me about 2.5 years ago while I was sitting on a chairlift and skiing. So it's kind of very close to my heart because this idea very quickly matured to a theory that we presented, and then in a quick succession, some of these predictions at least have been seen experimentally. And at this point, there's some ideas for applications of this topological state. So in these two lectures that I'm going to give today and tomorrow, I'll first review the theoretical part. Then I will talk about the experiment, which observes some of these predictions. And then tomorrow, I will finish with discussing some proposed applications. It's a work of quite a few people by now. A theory has been done mostly in my group. There's experimental work done in Philip Kim's group at Harvard, and we had lots of external collaborators both on theory and experimental side. Here's just before pandemic. I took my group up skiing to Whistler, and there are 3 of the main actors who then have done some of the calculations that I'm going to present today. So, okay, so here's the idea, which kind of can be thought of as a practical or specific realization of some of these general principles that have been discussed by previous speakers in this school. So let's think about a single monolayer of a D-wave superconductor, such as BISCO, for instance, which is one of the high-Tccuprates that actually can be exfoliated to a monolayer and is known to be a D-wave superconductor. And then we take another one, we twist it and stack it, and see what happens when we have this near 45-degree twist. And when I first thought about it, I had this inkling that this system should prefer to go into this time reversal symmetry broken D plus ID state. And there's a simple argument that I will go through that actually supports that, and we have several levels of modeling which also show that this is likely the outcome. So here's the logo of the talk. Now, looks like my pointer is no longer working, but is there an extra pointer that I could use? This always happens. Batteries don't last too long. Okay, we can swap that. Thank you. So this is a bit better. So this is going to be my logo for the rest of the talk, symbolizing this D plus ID superconductor, where here really the 2 D-wave order parameters live in the 2 different layers. So it's an artificially constructed, engineered structure. And what I'm going to try to convince you of is that in this time reversal symmetry broken phase, what you get is a topological superconductor which has a gapped bulk, and it has topologically protected chiral edge mode. It's a chiral phase, as was already discussed by several speakers. So important motivation for this work was this experimental work from Yang-Bo Zheng's group published in 2019, where for the first time in a 30-year history of the field, what they were able to do was to isolate a single monolayer of this cuprate BISCO under such conditions that it remained superconducting with high transition temperature after being exfoliated down to a single monolayer. And this is not the first time this was tried. People actually tried, but always failed until this point. And it's now understood why that was. Basically, you need to do this under very special conditions at low temperatures under inert atmosphere, because these materials are very sensitive to oxygen. as soon as you expose a monolayer to oxygen, it changes this doping level, right? You see here this O8 plus delta, and this delta has to be precisely set in order to get a superconducting phase. As soon as you expose it to air, this delta changes and it goes into insulating state. So normally, if you do that in air under ambient conditions, you don't get anything interesting. However, when you do it in low temperature environment in argon atmosphere in a glove box, then what you see here is superconducting. This is resistance, and you can see that I think blue line is bulk, red line is a single monolayer, and you see there's hardly any difference between a bulk crystal and a single monolayer. So once I saw this, I thought, well, people twist graphene. Maybe somebody can twist these materials. And just some other figures from this paper. They see for those who know about high-Tc, the superconducting dome as a function of doping, which here they can actually do in a single sample by electrostatic gating. And here's a spread of critical temperatures in various samples, blue for the bulk and red for the monolayer. And again, you can see that within a few percent they are in the same range. So this is nice. So what happens when you assemble two such monolayers with a twist? And the simplest way to look at this is, again, constructing the Ginzburg-Landau theory for such a bilayer. And I will walk you through this in some detail because this is a nice specific example of these general principles that have been discussed by other speakers. So here's the free energy. We have two complex order parameters for two layers, which I call phi1 and phi2. The free energy will have two pieces that are just monolayer pieces, and they should be identical. And then if you constrain yourself to terms up to fourth order, there's these three terms that I call A, B, and C that are allowed by symmetries that couple the two. And so it would look like this for two S-wave superconductors. The only difference actually at this level is that this B coefficient is required by symmetry to vanish at 45-degree twist. And that's the statement that at 45-degree twist, there is extra symmetry, which is non-crystallographic. It becomes a quasi-crystal. It has this D4D symmetry, and that disallows this term. Now, you can also argue that when you increase twist by 90 degrees, this B should change sign. And to lowest order, then you can assume that it has this dependence cosine 2 theta on the twist angle theta. So that's how the D-wave symmetry is incorporated in this free energy. OK, so now let's analyze this. Let's assume that these two layers are identical. And in that situation, you would assume that the order parameter amplitudes will be the same, but they can still, the two order parameters can still differ by phase, which I call phi here. So this is my ansatz, the common amplitude, which I will take to be real, and some phase difference phi. If you plug that in to that equation, what you find that it's these two terms on the last line that are important because they will depend on this relative phase. Whatever is on the first line does not depend on the relative phase. And you get two terms from here. The first one looks like a conventional Josephson coupling term, cosine phi, right? And it comes from this B term. And you can think of it as a transfer of a single coupled pair from layer 1 to layer 2, or vice versa. You can think of these psi's as creation-annihilation operators of a pair. So for instance, this term here would annihilate a pair in layer 1 and recreate it in layer 2. After this substitution, it leads to the conventional Josephson coupling term, which makes sense physically because Josephson effect is tunneling of single Cooper pairs. Now, the second term here comes from the last term. And that one can interpret as coherent tunneling of two Cooper pairs at the same time. You destroy two in one layer and create them in the second layer. And this gives rise to this cosine 2 phi term. Okay? And the prefactor I call script k, and it's given here. Now, the only other assumption that I will make is that this prefactor k is positive. And symmetry doesn't really give me that. However, most microscopic models would lead to this. Negative sign would give you these nematic phases. I will, for the rest of the talk, assume that this is positive, and this will give a chiral phase. So let's look at this what you may call Josephson free energy. And it's almost a high school level analysis, because it's just a competition between cosine phi and cosine 2 phi term. And free energy as a function of this relative phase looks like this. Various colors here correspond to different twist angles theta. So blue is small or 0 twist angle. And as I go from blue to lighter blue and then to red, I'm increasing the twist angle, where by large theta, I mean 45 degrees. That's the sort of maximal twist angle that you can make. So you see, something interesting happens. Initially, this free energy has just one minimum at phi equals 0. This is when the first term dominates, the Cooper, ordinary Josephson tunneling dominates. So you expect the two superconductors to be in phase. However, when this term is sufficiently suppressed by twisting, this goes to 0 at 45 degrees after all, then you see a phase transition where this one minimum splits into two inequivalent minima. And this corresponds to this time reversal symmetry broken phase that I mentioned and other speakers mentioned previously, because now the system has to take a stand. It has to decide whether to be in this minimum or that, and each one of them corresponds to one possibility that are conjugate under time reversal symmetry. So this is the basic argument, and it would predict that for a twist angle sufficiently close to 45 degrees, one should have this time reversal symmetry broken phase. Okay.
What's the value of k here?
Pardon me?
What's the value of k here?
The value of k, it's just a parameter at this level, and I'm assuming it's positive.
Wouldn't there be some, like, if k is too small, this doesn't really happen, the first term just always moves?
Yeah, so as long as k is positive and non-zero, this will always happen. But the range of the angles, twist angles for this time reversal broken phase will shrink. And that, that's what I'm going to mention right now. So what you can do, you can map out this equilibrium phase between the two layers as a function of twist angle. So I'm just tracking, again, using basically high school maybe pre-calculus algebra and trigonometry. I'm mapping the minima of these functions as a function of twist angle, and it looks like this. The preferred relative phase is 0 for small twist angles. Then there's this critical angle, phase transition, when I have suddenly two minima. And then I have this kind of behavior of this relative phase. So the time reversal symmetry is broken everywhere in this red area. And the size of this parameter k determines how wide that region is. When it's very small, then this region would be very narrow. And at this stage, we don't know what it is. It's just a parameter, but generically non-zero. OK, so one can add temperature to this. So these order parameters have a specific temperature dependence. And you can see, for instance, that this k depends on the amplitude of psi. So it will be temperature dependent. So one can extract the full twist angle temperature phase diagram. And it looks like this. There's this wedge here in the middle where you expect this time reversal symmetry broken phase. And the interesting thing is that at exactly 45 degrees, the time reversal broken phase extends all the way up to 1, which in this language is the native critical temperature of the underlying superconductor, which in BISCO would be those 90 Kelvin, right? So this is when I got sort of moderately excited because this would be a high temperature topological superconductor if you can actually make these samples. From the group theory point of view, this is a nice illustration of what Raphael was talking about, right? At this 45-degree twist, the representation, irreducible representation, is two-dimensional. So you have two degenerate order parameters because you have this non-crystallographic group D4D, and that's manifested by the system transitioning directly into this T-broken phase. Away from that special point, you have this other term. In the free energy, the symmetry is lower, so you actually have two subsequent transitions. You first go into the superconducting state, which is non-time reversal symmetry broken, and only then you break time reversal symmetry later on. Or potentially, if the twist angle is too small, you never go into the T-broken phase. So this is the Ginzburg-Landau analysis. And so this is solid. This Ginzburg-Landau analysis only depends on symmetry and one assumption that that parameter is positive. Now I'm going to tell you about some microscopic modeling. And one should view that as sort of toy models, which are relevant perhaps to Tccuprates, but the degree to which they describe the actual physics is highly debatable. So the simplest microscopic model of this type that you can write is basically a continuum Bogolyubov-de Gennes theory for two twisted monolayers of a D-wave superconductor. And the first line is basically just the normal state band structure. This is just individual monolayer dispersion, which I take parabolic for this toy model. Then I couple the two layers. I allow electrons to tunnel. And again, for simplicity, I'm taking a momentum-independent tunneling matrix element that I call G. And then you simply have the usual pairing term with D-wave symmetry here. Okay? And pictorially, what I'm having is something like this. So I have two superconductors at this point with circular Fermi surfaces, and the twist is incorporated by simply twisting their two D-wave order parameters as indicated by those two lobes. So this is the simplest model that you can write down. And let's see what can we learn from this. Its chief virtue is that it's easily solvable. It leads to a Hamiltonian, which is a 4x4 matrix in the usual Nambu representation. You have two blocks for two individual superconductors, and then you have a coupling between them. So this can actually be diagonalized analytically. You can find expressions, but they are not very illuminating for the eigenvalues, and you can learn anything about this model. So one thing that you can learn is you can construct the corresponding free energy as a function of relative phase. You can minimize it, and you can plot a similar phase diagram as I had from Ginzburg-Landau theory on the previous transparency. So this is this minimum phase between the two layers as a function of twist angle. The red line is the Ginzburg-Landau theory. The blue dots are just a result of this continuum Bogolyubov-de Gennes. Again, this G is just a parameter here, and I adjusted it in such a way that the critical angles are the same, but other than that, there's no other specific input here. So you can see that this theory predicts exactly the same thing. There's this time reversal symmetry broken phase near 45 degrees. What it allows us to extract, which Ginzburg-Landau theory did not, was the excitation gap. So I told you that in the bulk, this T-broken phase should be fully gapped. And from the microscopic theory, we can extract the size of this gap, which is these orange dots. And you can see that, putting in values that should be more or less realistic for BISCO, we're getting quite large gap, and this is probably unrealistically large, most likely around 20 MeV, and that's a consequence of having these simplifying assumptions like circular Fermi surface and so on. But nevertheless, this is what this toy model suggests. Okay, any questions? Yes?
So as written, the Hamiltonian seems to have tunneling independent of the twist angle, and I would expect
Yes. Yes.
How important and strong is this?
Yeah, so that effect is potentially very important. For instance, if you did a symmetry analysis of the underlying orbitals in the cuprate, you would find that this G should vanish at 45 degrees. Now, okay, so we tried to get to the bottom of this by doing, so this is the structure of BISCO, unit cell, right? It's a complicated thing, right? So we tried to get to the bottom of this by doing an honest to goodness DFT calculation for twisted structure with, commensurate Mohr unit cell. My coworkers spent lots of time and tears on this. And we got lots of band structures, but it's not really clear how to extract that G from those band structures. We just, they are way too complicated because you have these huge unit cells. There's just spaghetti everywhere. So one has to work with simple models, and the simplest of them is such that I take that G to be a constant, and there's some other issues that I can mention, but I don't know if I have time. You have another question?
Yeah, but I guess you can probably phrase the same thing. Just imagine that you do the very same calculation, but then assume that G is some function of phase.
Yes.
How strongly would the phase diagram, which is on the same slide, the gap, magnitude, and the change? Yeah, basically.
So basically, this gap here is proportional to G squared, right? It's G squared over delta to first order, right? So that's what it is. And if it's suppressed strongly, then this would be much smaller. And it seems like in real cuprates, if there is a gap, it's quite a bit smaller than what this would suggest. And that's why I preface this as a kind of toy model, which is broadly relevant to this problem, but maybe not quite one shouldn't take it as quantitative prediction. That's not the case. So we're just exploring what happens with two twisted D-wave superconductors here at the simplest level. Okay, so I told you about the excitation spectrum being gapped. So how do we see that? Well, again, within this simple toy model, we can actually zoom in near these nodal points of a D-wave superconductor and see what is the effect of being in the blue or red phase. So if I park my system in a blue phase where time reversal symmetry is unbroken, the low energy excitation spectrum looks like this. There's just two Dirac points which are ungapped. However, as soon as I get into this red phase, I see that the spectrum has been gapped, and this is that gap that I was plotting on the previous transparency. Also, well, how do we know time reversal is broken? Well, if we have two order parameters with some complex phase under time reversal, you get complex conjugation. So time reversal maps onto the other chiral phase, which would have a minus sign here. So whenever the free energy is minimized by phase that is different from 0 or pi, we are in a time reversal symmetry broken phase. Okay, I also mentioned that this phase was topological. So how do we know that? We know that from some older literature where people like Bob Laughlin and Ashwin Vishwanath and other people considered this D plus ID superconductor for some other reasons back in early 2000s. So there's calculations of a Chern number, but a very visual signature of this can be obtained when you put this model that I described on a lattice and you solve it on a long strip. And so this I like because it produces nice, colorful pictures. So what you can calculate is a spectral function in the bulk of the system. And for those of you who are not used to spectral functions, this is basically a local density of states that is plotted, because I have translation invariant system, is plotted as a function of momentum variable along this along this translation invariant direction. So in the bulk, what you see is that we have full gap. So around zero energy, there's no band, nothing really glows there, so it's a fully gapped phase. However, when I zoom in, I evaluate my spectral function at the edge, I see that this gap is now traversed by these right-moving edge modes. There's 4 of them, which signals Chern number 4, as you would expect for 2 layers of D plus ID superconductor. When I zoom on the other edge, I see, again, 4 modes, but now they disperse in the opposite direction. So this is the chiral phase. If I plot the whole spectrum, then this is something that maybe you're more familiar with. So this would be the band structure of the whole spectrum, not resolved spatially. So this shows the gap and also the edge modes. But this is a nice way of plotting that, because it really tells you that these edge modes live only at the edge. In the bulk, the system is fully gapped. Yes?
Were these results also obtained from the continuum model?
No. So I take the continuum model and put it on a square lattice. Because continuum model is kind of pain to deal with when you have edges. It can be done, but it's just easier to solve it on a lattice. And this is for exact 45-degree twist, by the way. OK, so yeah, so this is where this notion of a fully gapped state with edge modes that are chiral comes from. So I told you we've done several levels of modeling. So here's a sort of heroic effort of my 2 students who actually considered 2 lattices, square lattices with proper Fermi surfaces that are parametrized such that they look like what Fermi surfaces look like in BISCO. So for untwisted bilayer, you see 2 hole-like Fermi surfaces. And again, those of you who know about cuprates, this is how cuprate Fermi surfaces look like near optimal doping. And then when you start twisting, you see that in this unfolded full Brillouin zone, how the Fermi surfaces interact, and they look like this. So what one needs to do in this situation, one needs to find what are the commensurate angles where one gets a crystalline twisted structure. So this is the Moiré physics. And we're mostly interested in angles approaching 45 degrees. So these are the 3 commensurate angles that are closest to 45 degrees that we can actually solve within this lattice model. So this is a nice one, 53, that only has 10 atoms in a unit cell. When you want to model 43.6, which is pretty close, you already have to deal with a unit cell with 64 atoms. And then the next closest one has 338 atoms. And this we can solve self-consistently within a similar Bogoliubov-Dejean type theory, which now has proper Fermi surfaces and all that. Do I have some results from this? Basically, this confirms that picture, right? The near 45 degrees, depending on the strength of the interlayer coupling, you have this time reversal symmetry broken phase. Here's some results from that calculation near 45 degrees. So this is now more realistic. One finds a very small gap. So this is density of states, something that Stefan would be able to measure as a function of temperature. You see that at very low temperatures, there's this gap that arises from this time reversal symmetry broken phase. What you see here is a band structure on a strip now using the full Moiré physics, and that's why it's sort of less pretty, but maybe more realistic. And you can again see these edge modes. They are propagating either left or right. The color codes the distance from the center. So yellow is on the right, blue is on the left, so these are really edge modes. You find that there's actually two possible phases that you can get. It's Chern number 4, where there's 4 of them, and then there's also Chern number 2 phase, and it depends on the chemical potential. You can tune into a phase where basically one of the Fermi surfaces disappears, and you only have Chern number 2, but they are both topological and potentially interesting. Okay, so often when I was giving this talk early on, people would ask me, so is there a magic angle here? Because I'm now talking about large twist angle, right, 45 degrees. Is there something similar to graphene where you have these flat bands and interaction physics kicks in? And we were actually thinking about this in my group and doing already some calculations when suddenly this paper appeared on the archive. This is back December 2020, so about, now it's 4 years ago. No, 3 years ago. Group of Jet Pixley considered this problem. What happens at small angles? Do you have something similar to graphene flat bands magic angle? And it turns out there is something interesting, although there's really no flat bands. There's sufficient differences between this problem and graphene. Both have Dirac fermions, but in graphene, Dirac points occur at high symmetry points in the Brillouin zone. They occur at the corners. Here, in a cuprate, Dirac points occur in a generic point in the Brillouin zone, where the zero of the gap intersects the Fermi surface. So that's not a high symmetry point. And also, there's other differences between, one is a superconducting state, the other is just a band structure. So to cut the long story short, what happens, there's no flat bands, but there's still a magic angle which results from the collision of the two Dirac points. So as you twist the angle, keeping all the other parameters constant, what you expect to happen is that the two Dirac points actually collide and form a second order crossing, and then they split in orthogonal direction. Okay, so they come in like this, second order crossing, and then they part like that. So this is the result of this paper. And there's some interesting physics, because if you consider interactions are irrelevant for these Dirac points. However, they become marginally relevant for the quadratic crossing. So the phase diagram, in the presence of some residual interactions in the system, you would find that in the vicinity of this magic angle, actually you could find some gapped phase due to interactions that would also presumably break time reversal symmetry. Now, we have not, and nobody has done that really as far as I know. You can imagine, depending on what kind of interactions you can have many different symmetry broken phases here, but nobody has analyzed them in great detail. Here's a simple analysis that we performed. So we were assuming simply that the second strongest interaction in the system after the one that gives rise to D-wave superconductivity is in S-wave channel, in which case you would expect near this magic angle to have a subdominant S-wave order parameter being nucleated, and this is the phase diagram that you get as a function of twist angle and temperature. If you crank up that interaction strength as far as you reasonably can, so you would get, in addition to this D plus ID phase near 45 degree, you would get this bump here at low temperatures of D plus IS phase. Okay, and that would be the consequence of this sort of magic angle physics. There is no evidence so far for this phase, and likely, if it occurs at very low temperatures. Okay, so this was a review of the theory. Now I will talk about experiment. It was a very interesting journey for me, because this was during the pandemic, and first time I give a talk on this on the theory side. Still, it was a pandemic, everything was closed, so this was a Zoom talk. So I talked to some unknown people at some conference far away from my living room. And very next day, I get a phone call from Philip Kim from Harvard, and he said, oh, I heard you have this theory, and we have the experiment. So turns out already then they were exploring these twisted flakes. These are not quite monolayers, right? What they have, this is their experiment. They take a flake of Bisco, which is a few nanometers thick. So we're talking about thicknesses of tens of monolayers. They exfoliate it, twist it, and then they study. So this is the region where there's a twist between the two layers, and they study transport across that junction. So that's their experiment. And importantly, unlike some older experiments which also looked at these twisted junctions in Bisco, they are preparing their samples under those same conditions that give rise to monolayers that are high TC superconductors. So they do this at low temperature in argon atmosphere, very difficult fabrication step, but as a result, they get these atomically clean interfaces between the two twisted flakes. This is the TEM result, and basically the interface is right here between the blue and red arrow, and you can see that the crystal is really perfect all the way up to the interface, and then it changes its structure because it's rotated, but there's no really disturbance at the boundary. And so for the first time in history, what they saw just in this geometry is this suppression of the critical current between these two flakes as a function of twist angle. Right? So you would expect, just on the basis of basic D-wave theory, that free energy that I had on my second transparency, that this Cooper pair tunneling, this Josephson tunneling, would be suppressed at 45 degrees according to this cosine 2 theta law. Now, interestingly, people looked for this when, back in 20 years ago or more, when cuprates were first suspected to be D-wave superconductors, but nobody has seen this. People just saw, featureless, angle-independent critical currents, and if you read those papers, they conclude, cuprates are obviously S-wave superconductors because there's no dependence. So today, I think we understand what happened there. Basically, they did their maybe not exfoliation, but they prepared their samples in under ambient conditions, so the surface is very quickly oxidized, and there was enough disorder to completely wash out any signature of this. So this is the first time that you actually see this sort of first order effect. Now, already at that time, so this was like first time I talked to Philip, and he then sends me all this data. They saw this interesting behavior as a function of temperature, which they didn't understand. So this they understood. This you can open a paper from 1996 by Richard Clem, and there would be this prediction. But if you look at the temperature dependence, so this is the same critical current here, but plotted as a function of temperature. At zero twist, it does a reasonable thing. It decreases monotonically and then vanishes at the critical temperature, right? That's exactly what you would expect. But at these intermediate twist angles, they saw this non-monotonic behavior. The critical current first increases and then starts decreasing. And they found this generically at these intermediate angles. And they were very puzzled by this. You don't expect that because what temperature does, it breaks your Cooper pair. So you would expect there to be less supercurrent flowing. So how does this rises with temperature? And so this was the first thing that we were kind of able to help them with because it actually follows from basic theory that it should be like this. And we were quite happy that we were sort of maybe the first to point this out because it's a kind of interesting result. So I will walk you through this argument. And this can be understood on this, based on this very simple toy model. So you can take this toy model, and you can very simply calculate the current between the two layers, assuming there is some phase difference imposed by experiment. And what you find is that the expression for the critical current has the following structure. It's a complicated expression, but the structure is like this. You have a sum over all momenta in the Brillouin zone, or in this model, all momenta. Then you have product of the two superconducting order parameters, which is these two blue things. And then you have some complicated factor with Fermi factors and whatnot. But importantly, everything in this omega is greater or equal than 0. Okay? Now, this is all you need to understand this anomalous behavior that I showed on the previous transparency. So basically, it all comes from this prefactor here. So if you unpack it, you multiply these two mutually twisted order parameters, and they are just basically two cosine functions that are offset by this twist angle theta, right? Times some overall scale. Now, if I plot that, again, using high school trigonometry, what I find is that this product will be negative in these regions marked by red, right? And this is exactly these nodal regions, okay? It's just negative. You can see that, okay? So what you conclude from this is that at t equals 0, when you calculate the critical current, these nodal regions actually make a negative contribution to the critical current, okay? So that's the key point, because this product is negative, and then this omega function is always positive, okay? So what this, and this is actually what at t equals 0, or at low temperature, gives rise to this behavior where the critical current vanishes at 45-degree twist, right? Imagine you increase this twist angle, these red regions become bigger and bigger, and eventually at 45 degrees, they're as big as the regions that contribute positively, so that's where everything cancels, okay? So how does that explain the temperature dependence? Well, it's actually not difficult. So what does temperature do? Temperature breaks Cooper pairs, right? Because you have thermal excitations. Now, at low temperature, where do these Cooper pairs come from that get broken? Well, they come from the vicinity of the nodal regions, because that's where low-lying excitations exist. You can't excite at low temperature Cooper pairs with momenta somewhere where the gap is large compared to temperature. So basically, what happens is that at low temperature, thermal excitations lead to breaking of Cooper pairs exactly in these regions that contribute negatively to the critical current. And well, here's the full formula. It's not so complicated after all. This denominator is kind of ugly. But anyway, so if you model it based on this very simple model, it's not as dramatic as in experiment, but you see that this critical current at these intermediate angles always has a first increasing behavior, then there's a maximum, and then it starts decreasing. For some reason, in experiments, it's much more dramatic. And again, this is a toy model, just circular Fermi surface, BCS theory. High-Tccuprates are much more complicated. But the sort of qualitative feature, I think, is just basically this D-wave BCS theory. How much more time do I have?
16 minutes.
Good. So I'm pretty much on track. So this was a kind of first thing, and Philip was very happy when we presented it to him, because they really didn't know what to think about it. They thought something might be wrong with their samples, or apparently this kind of behavior is very unusual in Josephson junctions. Critical current always goes down with increasing temperature. So I had, of course, questions for him. Is there any evidence for this predicted T-broken phase? And initially, they didn't have any evidence, although what they tried was Shapiro steps. And so Shapiro steps, it's a kind of well-known old physics of Josephson junctions. And I will not explain to you how exactly you get Shapiro steps. So if you've never seen them, then I will not explain how they arise. But the measurement is the following. You take a Josephson junction, and you subject it to electromagnetic radiation in radio frequency range. And then what you find is that when you measure current voltage characteristic of this Josephson junction, you find these steps at integer multiples of the frequency of the applied radiation in proper units, so HF divided by 2E. And that can be understood from the dynamics of the Josephson junction. Basically, the Cooper pair can tunnel from one side to the other by absorbing one photon from the radiation field, and that's what gives rise to these steps. Okay, and you know, this has been known for very many decades. Now, okay, so they occur at integer multiples of the frequency, and what you see is a derivative of this IV where these steps show as these red bands. Okay, and the other axis is the power of the radiation that they put in. So okay. Now, the question then is, and what's a key input into the calculation that gives you these steps theoretically is the form of the free energy, or conversely the form of current phase relation, right? So if you have this conventional Josephson type free energy with one minimum, then you get these at integer values. However, it's a very simple matter to calculate what happens when you have this unconventional free energy with two minima instead. And what you find, and you know, that's when this term becomes small. This is our modeling. So this is Shapiro steps in a model of Josephson junction at 0 or small twist angle. However, when you get these two minima, what you find is that you get additional steps at half integer values of your frequency. And that's simply because you change periodicity of everything. And yeah, it's a kind of very simple, almost trivial result. But here's a more detailed modeling. And if you look at the actual experimental data, this is 44.6 degree twist. You see that there is faint lines at half integer. Yeah, if you have good eyes, you can see these. So this was the first sort of hint that there is some physics that hints at this T-broken phase. And importantly, these extra steps at fractional values of frequency, they don't occur at values of twist away from 45 degrees. There they see only integer value Shapiro steps. So this was kind of nice, and we were happy about that. Now, but this was the sort of smoking gun evidence that they only come up with more recently. So this is the Josephson diode effect. And let me take the last, I don't know, 6-7 minutes that I have by discussing this. So what is the Josephson diode effect? Imagine you have a Josephson junction like this. Normally, you would expect that the critical current of that junction should be independent on the direction of the current. Whether the current goes along the blue line or red line, you would expect that the response is reciprocal, right? However, it turns out this is not always the case. And whenever these two currents are not equal, that's called Josephson diode effect. So the junction is then non-reciprocal. And indeed, they found that this happens in their samples, again, when they are close to 45 degrees in these twisted junctions. The IC plus and IC minus are not equal. And importantly, this takes into account hysteresis. So this looks like some hysteresis, but what's being plotted here is IC plus and minus IC minus. So it's the same. Hysteresis is basically factored out here. This is not a trivial effect. So OK, they saw this. You can do neat things with this. You can construct a Josephson diode if you have a system like this. So imagine you put your bias current in between the two critical currents. So you park your bias current somewhere in between here. What you find then is this rectifier, right? If you apply current that has this oscillatory structure, but with value parked in between, and you measure voltage, you find that the voltage occurs only on one side of that cycle, And on the other side, there's 0 voltage, because on that side, the junction is perfectly superconducting. So this is like an ideal diode, which has a 0 resistance along one direction and finite resistance along the other direction. Now, why am I telling you all this? Well, it's an interesting effect, but also a key requirement for Josephson diode effect to occur is that the device has broken time reversal symmetry, right? You can show, and it's a very simple proof, that if you have a junction which obeys time reversal symmetry, because current is odd under time reversal, it has to be reciprocal. So this is a kind of smoking gun that there is something that breaks time reversal symmetry in these twisted junctions. And once again, it only occurs in junctions with near 45-degree angle. So let me give you a little bit of theory behind this so that maybe you understand better where this comes from. So this is the experiment. We're measuring a current between the two. Again, we model it by this free energy. D-wave symmetry gives this. Free energy looks like so. And if I take a derivative of this free energy, that's what gives me the current phase relation, right? So this is how the current looks like, which is just a derivative of this function, okay? Now, you can see right from this where the non-reciprocity comes in. So I assume I'm in a time reversal symmetry broken phase. I take one of these red curves and start from one of the minima of the free energy, which corresponds to 0 current, right? So I'm at this point. And now I start biasing the junction in one direction. The current increases up until it reaches this maximum, at which point, when I try to shove more current, the junction cannot sustain that, so it goes into the normal state. So this is the JC plus. This is the critical current in one direction, right? When I repeat the experiment, except I bias the current in the opposite direction, you can see that the current that it can sustain is much smaller. So this is where I get this non-reciprocity. Okay? So generically, you would expect for this model to give you this non-reciprocal behavior. There's some interesting caveats. So notice that there's always the other minimum, right? So if I repeated the same experiment starting from this other minimum on the other side, I would get the opposite diode effect, right? So, and again, this helped them understand, our experimental friends at Harvard. Once we explained that to them, that helped them to devise a protocol such that they can reproducibly always start the junction in one minimum. And you can do that by playing with currents. And then they see that indeed they can switch this diode effect from one to the other, and then they can play with two minima. Now, there was a bit of a hiccup. So the theory, interestingly, predicts that although at 45 degrees, in some sense, this violation of time reversal is the strongest, there should be no diode effect at 45 degrees. So let me explain that quickly, and that's going to be the last point I'm making. So at 45 degrees, it's this pi periodic free energy, which gives you a pi periodic current phase relation, right? And you can see that it's now symmetric around the minimum. So JC plus and JC minus are exactly the same. And this at first we didn't like, because Philip was telling me, well, we see the largest effect at 45 degrees. So yeah, it was a kind of a cold shower. Maybe it doesn't work in the end. But then they actually made more measurements, and this is the result of all their samples that showed diode effect. So this is the twist angle, and blue and red correspond to slightly different protocols by which they reproducibly get to these minima, and I don't want to discuss that, but basically whenever either blue or red is away from 0, that means there's non-zero diode effect observed. So you can see that for small twist angles, the diode effect is 0 within the error bars. Around 40 degrees, you start seeing something, and then you have fairly large effect between 40 and 45, but looking at this with a loving eye, at 45 degrees, it again dies off. So I would really be happy if we had 100 points here, and it showed some sort of dome behavior. But Philip tells me that it takes 2 to 3 weeks to fabricate and measure each of these samples, and his students want to graduate. So this is what we have. But this is more or less consistent with the prediction. At 45 degrees, this theory predicts that there should be no effect, and as best we can tell, this is what's happening. Okay, so Alex Sui is the hero here. He made all those samples and analyzed them. Okay, so this is where I'd like to stop. Some interesting art. Dali, two scientists pondering twisted high-Tccuprate superconductors. So I like that. Thank you very much. Oh, even back further.
The one with the this plot.
Mm-hmm.
Why are you saying if you apply negative current, the maximum current correspond to the minimum positive spot?
Okay. Yeah, let me go again through that argument. So maybe on this slide where it's even bigger, right?
Yes. Why
Yeah.
is this not on the negative side?
Okay, so it depends on where you start, right? So I'm assuming I'm starting from this right minimum, right? So when there's zero current, you have to be in one or the other minima, right, of the free energy. And the system chooses based on the history. And so I'm assuming you're in the right minimum. And once you make that assumption, then the two critical currents are different, right? Now, if you started from the other minimum, then they would also be different, but they would be opposite. The non-reciprocity would have opposite sign. So that's the tricky part here, right? So if you want to measure this effect reproducibly, you have to devise a protocol such that you know that you're starting from one of the minima every time. And then, indeed, you can see this reproducibly one sign of this diode effect. I don't want to explain how that's done because that depends on junction dynamics, but this is quite well understood. So they can actually do this.
Could you show us the slide with the experimental sample where you have the parents rotated and all the contents?
Okay, so that was kind of far away, so let me try to find it.
Yeah, this one. So you see that the chiral superconductor should appear in this overlap area, right?
Yes.
This is a sort of small fraction of the device.
Mm-hmm.
And then we push critical current essentially through one layer first. Then it goes into the area where we have this chiral state, and then it goes back into the standard wave back.
Yes.
So should we worry that essentially it's not exactly a current going through the chiral state, but it's a condensate 1, then this chiral break-in state, and then condensate 2?
Okay, yeah, that's a very good question, but the answer is no, we shouldn't worry. And the reason here is that there's a difference between in-plane superfluid density and interplane superfluid density, which is huge in these samples. These materials are very highly anisotropic, and so for all practical purposes, you never exceed critical current when it flows in plane, because that critical current is huge. You need to get a big generator to get above the critical current. Whereas interplane, those planes are very weakly coupled. So those critical currents are very small, and basically you're probing the interface, really. Yeah, not the bulk superconductor here.
Let me check whether I understood right the idea of this junction. If you have broken time reversal system,
Mm-hmm.
in principle you have two different states, right?
Yes.
The two, meaning that in principle I'm supposed to have two qualitatively different junctions. Whether
Yeah.
or in the
Yeah,
difference.
yeah, yeah,
Strictly
yeah.
speaking, I'm not supposed to speak of one junction, because it's sort of one of the two is just a junction which is simultaneously sort of the main wall between two different phases. This is kind of appropriate
Ah,
to think along those lines, because I can see what I mean.
yeah.
Since Z2 is broken,
Mm-hmm, mm-hmm. Yeah.
I can have, say, 1 and 1, or I have 1 and 2, and those are two different Josephson junctions. So apart from applied phase difference, I have this kind of two options.
Yeah, yeah.
Between 1 and 2. So how do you distinguish between the two? Because it looks like your plot corresponds to both simultaneously.
So if I understand, okay, yeah, sorry for this. I need to get back to where I was. So if I understand correctly, I think you're talking about two junctions being realized in the two minima of the free energy, right? Those are the two equilibrium states that are allowed.
The equilibrium state, but the junction is the junction between the two. And I have two situations. So the junction between two pieces.
Yeah.
Superconductor.
Yeah.
But since the time reversal is broken, the two pieces can be in one and the same state or in two different states, right?
So the relative degree of freedom is the relative phase difference, right? And this is the free energy for that relative phase difference. So what I'm saying is that the two states that are time reversal conjugate correspond to two different minima of that free energy. And
but now, if I have a Josephson junction,
yes.
I can have a situation where both pieces are in the same minimum or in different.
No, but it's a relative phase, right? It's a relative phase. There's only one phase that is that is a dynamical degree of freedom. There's some overall phase which is unphysical. We factor that out.
If I ask you a question, so here is a Josephson junction. Sorry, maybe I was slow. Here is a Josephson junction. And I ask a simple question. There are two pieces of superconductor, left and right. There can be two different situations. So suppose the kind of there is and with respect to each piece, if I just disjunct them, left and right, whether the two are in the same state or in complex conjugated states, one with respect to the other.
Okay, but to that I would say that it's only once you put them in contact when this time reversal symmetry breaking occurs. When you have just two disconnected superconductors, their relative phase makes no difference, right? It's like a phase in quantum mechanics, and unless you allow actually.
Okay. So you really, so so I got you, because I was thinking that you are talking of the Josephson junction between two pieces.
No. So importantly, the time reversal symmetry breaking occurs at the interface between them as a result of that. Yes. Yeah.
Oh, sorry. I think you were first.
I was wondering about the turn number. C was 4,
Mm-hmm.
and then it became 2. Maybe
Yes.
I missed. Was there an explanation?
Okay. So this is actually quite simple and well understood. So a single layer of D plus ID superconductor has a Chern number 2 or minus 2, depending on whether it's D plus ID or D minus ID. Now what we have is actually 2 layers. So nominally, you would expect to have Chern number 4 because each contributes 2 layers. However, based on the band structure, you can go into a situation such that you effectively have only single Fermi surface. So it behaves as a single layer as opposed to 2 layers. You just have bonding, antibonding, splitting between the two, and if your chemical potential is low enough, it behaves as a single layer. I don't think physically one can get into that regime easily, so it should be 4 for practical purposes.
So the theory that you developed over individual layers, but you mentioned that the experiment actually deals with flakes.
Yes.
But the original experiment also showed that monolayer effect was low.
Mm-hmm.
So do we expect that most of these results would just hold for any two bulk samples rotated?
Okay, yeah, that's an excellent question. So, yeah, so what happens for thicker flakes, right? So at the interface, all this physics of the relative phase, I believe, remains exactly the same as when we consider monolayers. So the relative phase would still be governed by this free energy. However, some of the other properties, like the gap and the edge modes, that's more complicated because those are only strictly speaking valid for a twisted bilayer composed of two monolayers, right? We've done some work to see what happens when you have thicker flakes, and basically what you find is that the gap just goes down the thicker the layer, because basically in the limit of two bulk samples, it's just a surface perturbation, so you cannot gap out the whole bulk. And I think it goes down algebraically as some power of the number of layers. Yeah.
All right. One more question.
Yeah. So for the fractional Shapiro steps, if it is just this like zone doubling thing, why are the half powers or the fractional steps so much bigger?
So that's why, and I showed you the best picture, right? So that's why the initial version of the paper was rejected from Science. Basically, that was the objection. And so, it's not quite 45-degree angle. And for technical reasons, it's apparently not easy to make exactly 45, where we would expect really all the steps to have the same amplitude. Our modeling shows that the amplitude of these fractional ones goes actually down fairly quickly as you go away from that. It, to some extent, depends on the assumptions about the dynamics. You have to assume something about the capacitance of the junction and so on. So it's slightly messy. But yeah, the answer is I'm not quite sure, because you see, according to the diode effect, which is this last figure. Oh, come on. Yeah, so there, it seems like there's quite a wide range of these angles where time reversal is broken, right? I don't want to put the number, but it's maybe plus minus 3 degrees, right? And the one with the Shapiro steps was within that angle, so it should be there. But yeah, that's the best they found. So many mysteries still. Yeah.